Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced this idea of the union and intersection of sets, and in this video what I want to do is introduce three new definitions of that of the absolute complement, the relative complement, and the Cartesian product of sets. Now looking at the first two, you can think of these, the absolute complement and the relative complement, as like the set theoretic version of minus that we have on the number system. So that is, we're going to kind of construct a way of taking away sets from each other. And the third case, which is the Cartesian product, is a way of basically taking two sets of kind of unordered data and mapping it to a new set that is now ordered, right? So it's a way of constructing ordered things from unordered things. And in fact, this is particularly useful in many different areas of maths, including linear algebra, calculus, as well as probability theory. It will be very useful in that setting as well. But before we move on to that, let's start with our first definition, which we said here was going to be the absolute complement of sets. So we need to start with our setup. And for the absolute complement, we must take two sets A and B where A is a subset of U. Then we say that the absolute complement of A and U is written as this A superscript C, and that's the set of elements in U that are not in A. So in other words, you can picture this as kind of think of U as this big set, and A sits inside it, and the complement of A and U is all the elements that are kind of in between A and U, but not including A itself. So it's like I've removed A from this big set U. And that's why it's important that they need to be subsets of each other. We need to have A as a subset of U. We think of U here as almost like our universe. That's why I've used this notation. So the absolute complement is normally only constructed when we're talking about subsets of each other. So let's look at some examples now of the absolute complement. So in the first case, we're going to take, as usual, a kind of simple example of sets. Here we've got U is the set containing the elements 1, 2, and 3. And A is the set containing the elements 1 and 3. Now we notice that A is a subset of U because all the elements of A appear in U. And that means I can construct the absolute complement of A in U. In other words, I take U and I remove all the elements that are also in A. In other words, I remove the elements 1 and I remove the elements 3, and all I'm left off with is the element 2. So if I write that out explicitly, what I just said there, that's A is a subset of U, and therefore A complement, or the absolute complement of A and U, is just the element 2. That is, I've removed all the elements from U that are also in A. Let's look at another example. So here we've got U is the real numbers and A is the rational numbers. Now, A is indeed a subset of the reals. We've seen this before. All of the rational numbers are inside the reals. And if we remove all the rational numbers from the real numbers, what are we left off with? We're left off with what are known as the irrational numbers. So in other words here, we can write that the complement is just given by the set of irrational numbers. And recall, actually, this is very much intuitive for how we constructed the reals. We constructed the reals by taking the rationals and completing them, completing them with all the numbers that weren't contained within the rationals. That was the irrational numbers. So it makes sense that if we remove all the rational numbers from the reals, that what we're left off with is the irrational numbers. We haven't really explored these too much, but some typical examples of irrational numbers are things like the square root of 2, pi, and e. And we'll look at them a little bit more probably next week when we start proving that those things are irrational. And in the third example, I want to take here as U is the integers and A is the naturals. Now we need to check that A is indeed a subset of U. Indeed, A is a subset of U because all the naturals are in the integers. The integers includes all the positive integers, all the negative ones, and 0. So the naturals sit inside the integers. So if I remove the natural numbers from the integers, what do I get? Well, I'm going to get 0 and all the negative integers. So that's going to be kind of 0, minus 1, minus 2, going on and on. So because they're subsets, I can construct the complement. And I can write that, in other words, in the following way, like I just said, this A superscript C as 0, minus 1, minus 2, minus 3, and I do my dot, dot, dot notation because I have an obvious prescribed pattern before, so I can just take away minus 1 in each step. And that's going to be the absolute complement of A in U in this particular case. But as I said, the absolute complement, it seems to be quite restrictive. We seem to be able to discuss sets that are subsets of each other. Is there a way in which we can construct a notion of complement or minus for any two sets? And that leads us to this definition of the relative complement. So Now, as I said before, unlike the absolute complement where we take sets that are subsets, we take A and B to just be any sets, and the relative complement of A and B is defined as this A, and we have this kind of sign here that means set minus. It's kind of like a minus sign, kind of slanted. Of A set minus B is equal to the set of elements X in A, but also not in B, such that they're not in B. In other words, we take all the elements of A and remove all the elements from A that are also in B. So let's look at some examples now, like before. And let's start with kind of two kind of finite simple sets here. We've got A and B. A is the set containing the elements 1, 2, 3, 4, and 5. B is the set containing the elements 1, 2, 5, and 6. And I want to remove all the elements from A that are also in B. I want to construct the relative complement of A and B. In other words, what elements are in B that are also in A? Well, the elements in B that are also in A are 1, 2, and 5. Right? 6 doesn't appear in there. So if I remove the elements 1, 2, and 5 from A, all I'm left off with is 3 and 4. So the relative complement of A and B, in other words, is the set containing the elements 3 and the elements 4, as we might expect. So let's look at another example. In this case, we're going to take A as the rationals and B as the reals. Now, we want to construct, in this particular case, we're going to take A set minus B, and we know this because of the fact that A is a subset of B here, that the relative complement is in fact the same as the absolute complement. So whenever we have that A is a subset of B again, the relative complement of A and B is going to be the same as the absolute complement of A. So in other words, this A set minus B, the relative complement of A and B, is equal to the irrational numbers like before, which was the absolute complement. And in the third example here, we're going to take A is the positive integers, so that's kind of 1, 2, 3, 4, 4 going on forever. So in other words, the same as the naturals, not including 0. And B is the negative integers. So that's what we're using for this notation with this superscript plus and superscript minus to mean positive and negative integers. Now, what do we notice here? We notice that the intersection of A and B is the empty set. In other words, A and B are disjoint. So because they're disjoint, it follows that the relative complement of A and B is given by A. Because there are no common elements. If I have A and I want to remove all the elements that are also in B, well, there are no elements that are also in B. So therefore, it's just A by itself. I can't remove anything off because the elements are disjoint. And this is true for any two disjoint sets. In fact, because it goes the other way around as well, if I take B set minus A, that is the same as B because B intersect A is also the empty set. Both A and B are disjoint. So that's a kind of more general rule that we can see here, that if the sets are in fact disjoint, if there is no overlap, then by taking them away, by definition, because there's no overlap, it means that I don't change my initial set. So that's our idea of complements, and that's kind of constructed this way of taking away sets. And the final thing that I wanted to talk about was the Cartesian product. So the Cartesian product, in this setup, we take any two sets, and we're going to call them A and B. Then the Cartesian product, which we write as kind of A times B, is this set here, which is this kind of, we bracket A and B together. So that's the set of kind of what we'll call these things in a minute, these two tuples, where A is in A and B is in B. So you can almost think of this thing, it might remind you a little bit of like coordinates that you've seen in school, where you have kind of an X and Y coordinate. And you'll see actually this is very much a good way of thinking about it. So that is, we take a set A, we take a set B, and we combine them together by just putting all the elements of A in one piece and all the elements of B in another piece. And we call these things, so the elements in this thing are called ordered pairs because the order matters, or two tuples. So we see that the order matters because A comma B is not the same as B comma A, unless A equals B in that case. But in general, if I flip the order, those two things are not going to be the same, right? If I put in 1, 2, that's not the same as 2, 1. And you can think of that as like points on the plane, right? The point 1, 2 is clearly not the same as the point 2, 1. So the order matters. So this is quite useful in the context of many different areas of maths to construct sets in this way. And we have a couple of comments to make about this. So the first thing is, unlike the intersection and union, the Cartesian product is a non-commutative product. That is to say that, in other words, A times B is not the same as B times A. And that follows again from the fact that the order matters. So unlike before where we had A union B was the same as B union A, and likewise for the intersection, this is not the same for the Cartesian product. So A times B, or A Cartesian producted with B, is not the same as B Cartesian producted with A. And we also have some additional notation to put here. So we sometimes use this notation A to the power of n to mean this A Cartesian product n many times, and the elements of this A to the power of m we refer to as n tuples, right? So like before above where we've got two sets, the elements in that are called two tuples. If we have n many copies of a set Cartesian producted together, then we call the elements of that n tuples. So let's see some examples and see if we can see in action some of these properties that we're talking about here in this remark. So let's take, again, we're going to take two simple sets here. We're going to take the set A is the elements, the set containing the elements 1 and 2, and B the set containing the elements 1, 3, and 4. What is the Cartesian product of A and B? Well, what we do is we take all the elements of A in the first piece and all the elements of, and kind of stick them together with all the elements of B in the second piece. So we write that, the Cartesian product of A and B, as the following. So it's this set containing all these ordered pairs. And what I've done here is to think about it in kind of an algorithmic way. You take the first element of A, and then you stick it together with the first element of B. So that is, we've got 1 with 1. Then we take the first element of A again, and stick it together with the second element of B. That is 1 with 3. Simultaneously, we do then 1 with 4, so that's 1, 4. And then we take the second element of A, which is 2, and then we can stick it together with each of the elements of B. So that is 2, 1, 2, 3, and 2, 4. So we've constructed here what is the Cartesian product of A and B. And we can also show that what happens if we construct the Cartesian product of B and B times A. So if we do it that way, now take all the elements of B individually and Cartesian product them with the individual elements of A. So you might seem that it's like that this is very similar, in fact, to kind of how you would kind of multiply brackets out when you've done multiplying brackets out at school. So going through the B times A example, we take the element 1, we fix that, and then we do 1 with 1, then we do 1 with 2, then 3 with 1, 3 with 2, 4 with 1, 4 with 2, and that constructs our set here for the Cartesian product of B times A. And notice, like I said before, that A times B is generally not equal to B times A, and we can see that in this example by thinking about what we said about the equality of sets. Recall that two sets are equal if they're each subsets of each other. And clearly these are not subsets of each other. There are some elements in common, for example, like the element 1, 1. But, for example, if I look at the element 2, 1 in A times B, that is not contained in the set B times A. B times A does contain the element 1, 2, but because 2, 1 is not the same as 1, 2, because they're ordered pairs and the order matters, these two sets are therefore not equal because they're not subsets of each other. So what about another example? So now let's take A and B to be the same set. Well, in this case, in fact, because A and B are equal, clearly it's going to be the case that A times B is going to be the same as B times A, or the Cartesian product of A and B is the same as the Cartesian product of B and A. So what do we write here? Well, the Cartesian product of A and B we write as this R2, so you might have seen this notation before. This is sometimes abused a little bit because we write R2 to mean lots of things. It could be meaning as a vector space or as a kind of a space with some more structure on, essentially what I'm saying there. But for now, we're just thinking of this as a set, and it's a set of ordered pairs where the pairs appear that A, the kind of first element is in the reals and the second element is also in the reals. And this is really just a formal way of writing how to construct the kind of plane of points that you draw in school. So in other words, the elements of this can be visualized as points on the plane. So this is exactly what you draw as the kind of Cartesian plane in school, where the kind of x coordinate is the A coordinate and the y coordinate is the B coordinate. So that's how you can visualize the Cartesian product of two copies of R. And you're really thinking of the first real number line, the A piece, as the kind of x-axis, and the second real number line as the y-axis. And you see here, obviously, again, immediately, that the order matters, as I kind of said before, that you see that 1, 2 is not the same as, say, 2, 1. And you can think of that as because those 2 points clearly don't lie at the same point on the plane. So that's where we're going to finish off this video now. And actually that's everything that we're going to talk about in the context of set theory for this course, or this particular part of the course. And the next thing we're going to move on to now is we're going to start talking about how to use all the things that we've introduced in set theory, all the logic we've introduced, and start proving some actual mathematical statements now, as well as talking about some types of statements that appear and techniques that you can use to prove them, a bit like things like proof by induction that you may have already seen in the calculus component of the course, but we'll talk rigorously about how to construct a proof by induction and many other types of proofs like direct proofs and indirect proofs and things like this. So the next video, what we'll talk about is we'll talk about kind of a very big picture about how the kind of idea of mathematics works, or how we construct things in mathematics, what's our setup in mathematics to start proving things. And next week we will talk formally about how to actually start proving particular statements in maths. So once again, as always, I remind you to look at the notes on the Moodle page and to attempt any problems in the module handbook that relate to this video that you just watched now. So thanks for watching, and I will see you again in the next video. Thanks, bye.